In this video, we're going to talk about what is one of the most important principles in calculus as far as the applications of the material go. And this is the finding of the minimums and maximums of a function, also known as the extrema, or critical points. Now, we're going to differentiate between all of these terms in a little bit. But for now, let's just consider what we are looking for and how we're going to do it. Let's say we have some function here, where this is x and this is f of x, and I'm just going to draw a function here that looks something like this. And this function has several of what we call critical points. A critical point is defined as any point on f of x such that f prime of x at that point is equal to 0. Now, we'll come back to this definition. Let's consider what that means in terms of implications. Let's say I wanted to find a relative maximum for this curve. In other words, I want to take f of x and I want to know the value of x that produce, the values of x, that produce the highest and lowest values of f of x. Now, looking at this graph, you might say and you might realize that there isn't actually a complete highest value or a complete lowest value because this graph is going to go up indefinitely, down indefinitely, thereby producing continuously higher values to the right and continuously lower values to the left. What we could do, though, is find what are called relative maximums and minimums. And in certain cases, like a parabola, it's a little bit more significant. But in this case, we could agree that this point right here is a local maximum. And what I mean by local maximum is it's the maximum relative to the points around it. In other words, the function is lower in values both on the left and on the right. So we could take a look at the function and say, well, up to here it is increasing. From here on it is decreasing, but at the very top it is a maximum. So at this point, the key question is, what is the slope of the line tangent to the curve at this local maximum? And you should be able to recognize that the slope here is 0. And you should realize that any point that is a local maximum or a local minimum is going to have a tangent line with a slope of 0. So we have a slope of 0 at the max and a slope of 0 at the min. Now, of course, we know that the slope of the tangent line is represented by the derivative function. So here again, we can see the same thing at the minimum of this function. We have a decrease to here, and then an increase. This is a minimum, and again, the slope of the tangent line is 0. So since the slope of the tangent line is 0, so since we know that the derivative represents the slope of the tangent line, we could say that at these points, f prime of x is equal to 0. And that is precisely how we are going to find our extrema or critical points. Now, naturally, again, these are local extrema, and we're going to have to either look at a graph or do a little bit of interval analysis in order to figure out which points are maximums and minimums. And for this, we're going to have to remember very clearly that for a maximum, we increase first and decrease. and for minimum we decrease to the left and then increase to the right. But we'll talk a little bit more about this with a couple of examples. So let's look at the definitions of relative extrema. Relative extrema are the extreme values on a function relative to the points around them. In other words, what we saw on the previous page, this is a relative maximum over here, even though there are values on the function that are higher that are over here. And this is a relative minimum over here, otherwise known as a local minimum, or here a local maximum, even though there are lower values of a function over here. Now, on certain graphs, like a parabola for instance, a relative maximum may also act as what's called an absolute maximum, which means that the absolute highest value. So here, a local maximum, which clearly occurs right here, there are no values at any point on this parabola that are higher than this. Or if I draw a parabola that's upward facing, again, this right here would be the absolute minimum. Again, we'll talk about absolutes a little bit later in this video in detail, but it just simply means that there are no values lower than this anywhere in this parabola. So if I go lower, no values exist, and if I go higher here, no values of the function exist. So that would produce a point that's outside of the range. But again, something like this would produce both a relative minimum that's not an absolute minimum and a relative maximum that's not an absolute maximum, both of which will have slopes of 0, tangent slopes of 0, and of course that would imply that the derivative at this point is 0. Okay? And this is kind of important, the second and third point here. A function increases from the left side until a relative maximum, then decreases right of the relative maximum. So just imagine this kind of shape. We have an increasing function here, and then a decreasing function here. Well, we're going to have a maximum somewhere over here. So the important thing to realize here is that here we have a positive slope, which means that f prime of x at these points is greater than 0. And here we have a negative slope, which means that f prime of x, the derivative of this function, is actually less than 0 on these points. And the opposite applies to a relative minimum point. So here we have a max. If we have a min instead, the function is going to be decreasing until we hit that min, and then it's going to start increasing. So over here we're going to have a min. So here again, this is going to have the opposite effect. We're going to have f prime of x is less than 0, so a negative slope, and then f prime of x is greater than 0, so a positive slope. Let's examine what this is going to look like on an actual. Excuse me. Let's examine what this is going to look like on a actual function. So the example we're going to look at here is actually x cubed minus 6x squared plus 9x minus 1, which is graphed here. And the question would read something like, find all relative minima and maxima of the function. As we get a little bit deeper into this topic, we're going to encounter problems that ask us to find all the critical points and then differentiate between them. For now, let's have a look at the basics. So we already know that at any given relative extrema, at a maximum or a minimum, the derivative will equal 0. And that's what we're going to use to find the x values. Now, if we look at the graph, we should be able to recognize that this right here is a relative max, and this right here is a relative min. Let's confirm this using calculus. So what we have is we have the function, which is f of x is x cubed minus 6x squared plus 9x minus 1. And we're going to take the f prime of x, which we'll take using the power rule, 3x squared minus 12x plus 9. And what we're going to do is, since we know that the relative extrema will occur wherever f prime of x is equal to 0, we're going to set f prime of x equal to 0 and find the values of x that make that true. So I'm going to factor out a 3, be left with x squared minus 4x plus 3, and then we're going to factor that and get x minus 3 times x minus 1 equals 0. And then we're going to set each factor equal to 0. Obviously 3 cannot equal 0, so we're just going to go ahead and reject that immediately. And then we're going to set x minus 3 equal to 0, which would produce x equals 3. And then we're going to set x minus 1 equal to 0, which would produce x equals 1. Now, we now know that at these points, the slope of the tangent line to the curve equals 0, which means they are critical points. We don't know if they're maximums, minimums, or neither yet. There is a scenario in which it could be neither. Well, in order to find out which it is, we need to invoke something called the first derivative test. What we do in order to conduct the first derivative test is draw a number line and label it f prime of x. And now we know that at these 2 points, x equals 3 and at x equals 1, the derivative is equal to 0. And of course, visually we can tell which one the maximum and minimum is, but sometimes we're not going to have access to the graph or a graphing utility in order to find that. So we need to know how to do this using calculus, using just calculus and algebra. So we know now at these points, x equals 3 and x equals 1, that at those points the derivative is exactly 0. Well, looking back here, we know that a maximum is going to have a positive derivative left of it and a negative derivative right of it. And a minimum is going to have a negative derivative left of it and a positive derivative right of it. So we could use that to our advantage, knowing that the derivative can only change sign when it passes through 0. So I'm going to label 1 and 3 as what we call the cut points. And the cut points are anywhere where f prime of x is equal to 0. There are also scenarios where you're going to need to include a cut point for where the denominator equals 0. That is something that we're going to find a little bit further down the line. So, what we can do is find whether or not the derivative is positive or negative in each of these intervals. So for the left interval that is left of -1, I'm going to go ahead and pick a number. And I'm going to pick the number 0 because it's easy to work with. For the interval 1 to 3, I'm going to pick the number 2, and for the interval 3 or greater, I'm going to pick the number 4. And what I'm going to do is I'm going to go ahead and substitute those values into the derivative and identify that f prime of 0, derivative's up here. It's 3x squared minus 12x plus 9. And we get 9. So we have a positive number here. So we can say that f prime of 0 is greater than 0, so we have a positive slope. So at this point, the function is increasing. And we can assume, since at no point does the derivative cross 0 until 1, that the function is increasing for this entire interval. Now, just as a quick side note, you may want to go ahead and cross out this point afterwards, because a lot of students tend to get confused with the intervals and the points that they need to input. These points are arbitrary. We choose these, the 0, the 2, and the 4, to represent an entire interval. If I chose -1, 2.9, and 1,000, I still get the same exact answers. I'm just picking numbers that are a little bit easier to work with. So at this point, the function is increasing. Let's substitute it into 2. F prime of 2 is 3 times 2 squared minus 12 times 2 plus 9. And we get 12 minus 24 plus 9, that's negative 3. So at this point, the f prime of 0 is less than 0, and therefore the function is decreasing because we have a negative slope. So this is negative, and the function is decreasing. So now we know that this point right here, the 1, that has to be a maximum, because the function is increasing, then decreasing. Okay. Now we need to check 4, and we fill in f prime of 4 equals 3 times 4 squared minus 12 times 4 plus 9, and that's going to be 16 times 3, that's 48 minus 48 plus 9, so we get 0 plus 9, which is 9, and again, this is going to be positive, just like this one, and it's going to be positive, so that means f prime of 4 is greater than 0. I just realized I put a 0 here where there needed to be a 2. That was the f prime of 2 before, that was negative. Here the f prime of 4 is 0, which means that the slope is positive at that point and presumably on that interval, and thus the function is increasing on that point. So here we're going to have a minimum, because we have a function that is decreasing prior to that and then increasing subsequently. So we have a max at x equals 1, and a min at x equals 3. Now we will go a step further here and actually take the original function, which is f of x is x cubed minus 6x squared plus 9x minus 1, and go ahead and actually get the exact values. So we can just go ahead and get f of 1 to get the y value. That's 1 cubed minus 6 times 1 squared plus 9 times 1 minus 1. So that's going to be 1 minus 6, that's negative 5, plus 9, that's positive 4, minus 1, that is 3. So we'd say that f of 1 is 3, so there's a relative maximum of 3 at x equals 1. And then we could say that there's a relative minimum of whatever f of 3 is, so we're going to get f of 3, that's 3 cubed minus 6 times 3 squared plus 9 times 3 minus 1, that's going to be 27 minus 6 times 9 is 54, so negative 27 plus 27, that's 0 minus 1, so we get negative 1. So there's a relative minimum of negative 1 because f of 3 is equal to negative 1 at x equals 3. The point thus being 1, 3, and 3, negative 1, and we can look at those 2 points and say, well, this right here is most definitely 1, 3, and this here is 3, negative 1, to confirm our solution. Now we can actually get a little bit more information out of this. We can also say that the function is increasing on the interval from negative infinity to 1, non-inclusive. Because we know that the function is increasing through this entire value because the derivative is positive, or 3 to positive infinity. And we can also say that the function is decreasing on the interval 1 to 3, which again, some questions will request that, some questions will not. Once we get through concavity, we're going to see what's kind of a general question for this unit. So now let us take a look at something called absolute extrema. The absolute extrema are the absolute highest and lowest function values on a given interval, and this is key. We will only be dealing with absolute extrema on an interval. Some functions may have absolute extrema on an all real numbers interval, but we'll treat those as relative extrema. Something like a parabola, where that's the absolute max. You wouldn't be asked to find the absolute maximum. Write that on meter. You would not be asked to find the absolute maximum of a function without being given some sort of an interval. And lastly, the big difference between the absolute and the relative is that the absolute extrema on an interval can occur at points of relative extrema or at the endpoints of the interval, which means we need to test the endpoint values to see if they are higher. Now, throughout this, we need to remember what we're looking for. The absolute extrema are the actual highest and lowest function values in an interval. So let us imagine that we have an interval like this, from A to B. And I draw a function that looks something like this. You should be able to tell me that it appears that the absolute minimum is here, which occurs at a relative minimum, and that the absolute max is actually here. Because even though there's no point here at which the derivative is going to be equal to 0, I'm just asking you what the highest value on the interval is. So I could say that the f of b needs to be tested, the f of a needs to be tested, and then any points c where the f prime of x is 0, and this is also the lowest value on the function, so this is also the absolute minimum in addition to being the relative minimum as well. This is best described with an example, so what we're going to do is we're going to go ahead and do an example of this on this page, and what I've done here is I've actually copied two identical functions in the sense that it's actually the same function, but I'm using different intervals. Let me just correct this interval here. This is actually -2 to 3, not the same as the -3 to 2 that we have over here. So here, you should be able to tell me that when I'm dealing with the interval from -3 to 2, this is apparently my absolute minimum, because there is no lower function value at this point. And my absolute maximum appears to be here. So what we're going to do is we're going to verify that using algebra. So the first thing we're going to do is we're going to find the relative minimums. So step one would be to find the relative, not just minimums, find the relative extrema. And in order to do that, I have to take the derivative, f prime of x, which is going to be 1/3, so just x squared minus 2. And we're going to go ahead and set that equal to 0. So x squared minus 2 equal to 0. So x squared is equal to 2, which means that the the relative extrema are going to occur at plus and minus the square root of 2. Now, we can actually invoke a decimal here if we want to get the square root of 2. That's 1.414. And we can use some decimals, some radicals. I'll show you a little bit of both in this case. So it's 1.414. So plus and minus 1.414. And what we're going to do here is say, well, wait a minute, I don't really care whether these are relative maximums or relative minimums, each of these points, I'm just going to use them to find the highest function value. I know that the only points at which the absolute extrema can occur are these here, and the two endpoints, which are -3 and 2, because if the function just continues higher or lower at those points, well, as we can see here, we have what appears to be an absolute minimum there. So let's verify this. All we have to do is determine which of these four values produces the highest function value. So remember that our f of x here is 1/3 x cubed minus 2x plus 1. So I'm just going to go ahead and sub each of these values in. I'm going to start with the endpoint, -3, the left endpoint, -3. So that's going to be 1/3 -3 cubed minus 2 times -3 plus 1. -3 cubed is -27, so this is going to be -9 minus, plus 6 plus 1. It looks like -2. So I will say that at f equals at f of -3, we have -2. So f of -3, to simply put, I'm just going to highlight that because that's one of our possible extrema. And the next one I'm going to sub in here is going to be f of negative radical 2. If you wish to use the decimal 1.414, you can do that. And in this case, for simplicity's sake, we are just going to use the calculator to get that value. Forgot the negative there, you don't want to forget that. I'll say again, I forgot to put the negative in, bear with me here. Calculator tool seems to be operating quite slowly. I'll put that in, and it looks like 2.88 is what we get here. So I'm going to use an approximate here, 2.88. So we'll say that this is f of negative radical 2 is 2.88. So now right away we should know that there's no way that the top one here can be a maximum, and there's no way the bottom one here can be a minimum, because we already have values that are higher than that, or lower than that in this case. So f of radical 2 is just going to be 1/3 times the square root of 2 cubed minus 2 square root of 2 plus 1. And I'm just going to call up the calculator here again. Fortunately, this should be a little bit easier. And then all I have to do is remove these two negatives. And let's get an answer there. And it looks like negative 0.886. Okay, so this is another possible value here. And then the last one we're going to put in is the 2, which is our other endpoint. And that's going to be 1/3 of 2 cubed minus 2 times 2. plus 1. So it's going to be 8 thirds minus 4 plus 1. So we'll make this a 3. Minus 4 plus 1 is the same thing as negative 3, which will then change to 9 thirds, and we'll get negative 1 third. So if you, again, want to stick with the decimals here, you can certainly do that. F of 2 is going to be equal to negative 0.33 repeating. So those are our 4 possible extrema, because these two right here, the two I'm going to highlight in blue on the side, these are endpoints, and the other two are relative, max and min. So all we have to do is look for the highest value. Well, this is the highest value here, the 2.88. So we have an absolute maximum here. And then we have the lowest possible value is right here. So it looks like the lowest possible value is negative 2 at x equals negative 3. And that's exactly what it looks like on the graph over here. And then we've got a value slightly under 3 of 2.88 at negative radical 2 or negative 1.414. That looks to be correct over here. Now, let's see how this changes when we change up the interval. Let's say now our interval is negative 2 and positive 3. Now, what we can see here is that the relative max and the relative min aren't going to change. Right now I'm using these as relative maximum and relative minimum. Now it looks like here we had a relative minimum that ended up being irrelevant. What it looks like is that we're going to have an absolute max over here. And it looks like the relative minimum is going to become the absolute minimum here because I don't see any values lower than that. So let's verify this again using some algebra. We already know that this point right here from doing, this is the same function, remember, is going to be negative radical 2 and then looks like 2.88. We did that before by finding the relative maximum and then testing the exact value and finding that. In that case, that was the absolute maximum. And then we already know that this point is going to be radical 2 and then negative 0.886. So again, that's going to be a relative minimum. In this case, it looks like the absolute minimum. So in this case, we already know f of negative square root of 2 is 2.88, and f of the square root of 2 is negative 0.886. And then all we need to do is test our two endpoints. So let's test negative 2. That's going to be 1/3 times negative 2 cubed minus 2 times negative 2 plus 1. And that's going to be negative 8 thirds plus 4 plus 1. So negative 8 thirds plus 5. That 5 is 15 thirds. And we've got positive 7 over 3. Again, if you prefer to decimal, in this case for comparison purposes, that's going to be 2.33 repeating. And then lastly, we're going to have f of 3. That's the endpoint over here. And then the f of 3 is going to be 1/3 times 3 cubed minus 2 times 3 plus 1. And that's going to be 27, so 1/3, that's 9, minus 6 plus 1, that looks like 4. So we could say that the f of 3 is 4. So our minimums and maximums, or minima and maxima, could occur at any of these 4 points. Well, it looks like, in this case, the highest value is the 4. So on this interval, even though it's the same function, the endpoint produces a higher value than the relative maximum. So the absolute max is going to be 4 on this interval at x equals 3. And then the absolute minimum is going to be the lowest value, which in this case is going to be the square root of 2 for the x value, and the function value is going to be negative 0.886. So we've got the same exact function and simply two different vantage points, two different intervals that we're using producing totally different results, with the only thing that's shared is the relative minimum, the relative maximum. The absolutes will vary with the function. Thank you for watching, and have a good rest of your day.